right, here we go. The very last lecture of AP Chemistry. Well, the last packet. It's going to probably be about 3 or 4 videos. But we are on the final concept, which covers 2 major ideas. That being, what happens when cell potential is not under standard conditions, and then electrolysis, which we dabbled a little bit with, and then talking about doing some conversions within that. So you finish with some pretty cool quantitative stuff here. All right, so this first idea is somewhat complex, so we're going to go through it slowly just to make sure that we can get a good understanding of what we're talking about here. Okay, first of all, it's very important to know what the standard conditions are. We talked about that last lecture, didn't emphasize it very much, but here you really have to use it. We have to know that under standard conditions this is a 1.0 molar. And we also have to know that the pressure is 1 atmosphere and the temperature is 25 degrees. So you're going to circle or highlight those 3 things. So if you had a solid with an aqueous ion going to an aqueous ion with a solid, and you're writing the equilibrium expression at any given moment in time, so it's not at equilibrium, or it might be, but most of the time it is not when you use the term Q, if you will recall. If the concentrations of these are both 1 molar, you can see QC, the equilibrium constant, will be 1. And the value of QC, or if it was a gas, QP for partial pressure, and it would always have a value of 1. Now, non-standard conditions. Kind of goes without saying, these first 3 things. They're not at 1 molar, they're not at 1 atmosphere, and the temperature is not 25 degrees. Any one of those 3 will throw off the values, those, and those we looked up, those are given reduction potentials under these perfect conditions. So if the concentration of the reactants decrease and the concentration of the products increase as the reaction proceeds. So you just got to remember that you're going to get less and less of what's on the left side, more and more of what's on the right side in these reactions. Cell potential decreases as the concentrations of the reactants decrease. So underline that statement right there, because what's going to happen is you're going to keep doing that until E0 of the cell equals 0.00 volts. So to use an example here, here the equilibrium lies far to the right, so your equilibrium constant is going to be very, very large for this given reaction, because that's what you want, is you want something that's going to continually react and continually charge your battery. Okay, to be clear, we're talking about voltaic cells here on these types of problems. So the cell potential will decrease. So highlight that. It decreases as reactants turn into products and as the system approaches equilibrium. All right? When that happens, Q equals K. That's that rare case where it actually, we're right spot on at equilibrium. Then you have a 0.00 voltage as a cell potential. In other words, the battery is dead. That's the bottom line here. It reaches that point. It's kind of, if you think about it, it's going down that hill, and then it just gets to equilibrium. And then remember that little graph with the ball rolling down the hill. So you have a system like this. Here's copper ions in some solid nickel. Now that would make a decent battery. You could do the calculations on that if need be. But if you could figure out a way to add more Cu plus to the system, that's going to drive this to the right. And the copper concentration becomes greater than 1 molar. So at standard conditions, it would be 1 molar. And then Q would become less than 1 because you're going to be heavy on this side. So it's further away from K, and therefore it'll drive that forward reaction then, and the voltage will increase, highlight, the electron flow or current, which is our ultimate goal here, will increase as well. And it will work for a longer time due to this excessive supply of Cu plus 2. Because when you start to run out of that, then it's time to replace your nickel-copper battery. Okay? So that's the mechanics of what's going on here. Now, this has Le Chatelier written all over it here. Okay? So if you're going to remove copper, what's going to happen is that will slow down that forward reaction. It'll get less than 1.0 molar. So Q will then be greater than 1 because you have taken away some of the stuff that will be on the bottom of the equilibrium expression. The voltage will decrease. Okay, so removing this, voltage will decrease. Highlight, underline. The electron flow will decrease by removing one of the reactants. All right? And the cell will not work as long due to removing that copper. So that's kind of the driving forces. Now, you can also do this with products. If nickel plus 2 is added to a system, it'll get greater than 1. So as this builds up, this Ni2, it actually slows down your battery again. The voltage decreases, so adding this product, you will have a decrease in voltage, and you will have a decrease in current. So you don't want to add on that side. What you do want to do is remove one of the products to drive that forward reaction, making the concentration of the nickel less than 1 molar, and it'll increase that forward flow, which will give a increase in your E0 of the cell, and you wouldn't really call it E0 of the cell because it's not at standard condition anymore, so just E cell, and then the electron flow also increases at that point. Okay, so we've kind of talked about, 4 different scenarios. You add and remove here. You add and remove there. And I believe it's, this slide can show sort of a neat little graphic showing if you decrease this, that would decrease the voltage. And if you decrease this, it would increase the voltage. And those things are going to kind of counter each other if you think about it. And the E0 of the cell, please add a plus in front of that. Be consistent, please. So if you look at the ratio of the nickel product to the copper ion reactant, equals Q1, and at standard conditions it was 1 over 1, and when you did this, it becomes 0.5 over 0.5, and that's the same thing. All right, so what happens is the voltage stays the same if Q does not change. So it would still have, this one right here would still have that same voltage. So you can draw a little arrow right there and draw a little arrow right there. They both would produce the same voltages. So a lot of times these changes in concentration from standard, if you have the same amounts on both sides, you'll get the same potential, because it's always about a difference in the need for electrons. Now, this is a very good summary. I don't think I've asked you to do this yet, but we're going to highlight each statement and go over each statement. And then you're going to say, if you want a good summary of EMF, the electromotive force under standard conditions, when it's in non-standard conditions, this is a great summary. Okay? So, as a cell approaches equilibrium, the magnitude of the cell potential decreases until it reaches 0 at equilibrium, where Q equals K. And then you can write the word dead in there too for your battery. Okay? Now, deviations from standard conditions where Q is less than 1 will increase the cell potential. I think it was easier to understand with that chemical reaction, but just get that idea. Q is less than 1. You'll want to jump back there. That drives that forward reaction, and then you get more electrons in a better battery. Deviations where Q is greater than 1 are going to mess up your battery. Okay? And they're going to slow down and decrease the cell potential. And deviations from standard conditions where Q equals 1 will not change the cell potential. We just talked about that right there. They're deviating from standard conditions, but Q is still equal to 1, so then that does not change the cell potential. Okay? So that was an understanding of what happens when we're at non-standard conditions, and we'll continue that on with changing the concentrations on our next slide, or on our next video. Okay, so this is the end of lecture 1 of this part of the packet.